Swayam Prabha. Digital India. Educated India.
Dear students, in our previous lectures, we have looked into simplex method as well as we got introduced to this problem of duality. So, if you quickly recall, we learnt about few examples that how we will deal with primal problems, how we will deal with dual problems and what were their implications. So, here I present a very quick recap of the mathematical notations that we already introduced. So, in case of primal simplex, we were dealing with problems of the form that we have to maximize z equal to c transpose x. Remember that this both x is a vector and this c happens to be matrix of coefficients. So, although I have written it in the compact form, at the end you can imagine them to be looking like the exact equations that we typically deal with while working on the optimization problem. Since we introduced simplex method for linear problem, this form also satisfy the condition of linearity strictly. And it is subject to ax equal to b and x greater than equal to 0. We learned that ax less than equal to b as one of the cases, ax greater than equal to b as another case, and we realize that the simplex method, which originally has been designed for constraints like maximize some function subject to less than equal to constraints, can be generalized or adapted to equality constraints as well as greater than equal to constraints with certain adaptations. We learnt something called as phase 1 and phase 2 methods, where in phase 1 we will write another equation such as w is equal to y1 plus y2, where y1 plus y2 happens to be artificial variables. In phase 1 we will eliminate these artificial variables and then we will proceed to phase 2 as usual when we are dealing with constraints of equality type or greater than equal to type. But overall, summary remains that we will introduce a slack or artificial variable to get initial basic feasible solution. We were calling it basic feasible solution because we would choose certain variables as non-basic and force them to be 0, and few variables will be chosen as basic, that is those variables which we do not select as non-basic variables automatically becomes basic variables, and then we try to express our equations in canonical form always. The beauty of canonical form was that if you have your system of equations written in canonical form, in each row one basic variable would be present with one coefficient. So, RHS of the tableau will exactly give us the solution. So, it would make it easy to check whether we are having feasible solution or non-feasible solution. Now, in case of primal problems, we were talking about feasibility in two terms. That is, all the variables, including slack variables, should be greater than equal to 0 and all the constraints should have been satisfied. Now, note that in case of primal formulation, objective function has no decision whether your solution is feasible or not. It is solely guided by the constraints as well as the greater than equal to constraint that we put on all variables. Whereas, when we went to the dual form, the objective function itself became part of the constraint and the resources that we had, ax equal to b, b itself became part of the objective function. And then constraint, the new constraint in dual, which is related to the coefficients in primal, would have say in the dual feasibility. So we will take advantage of going from primal to dual form to speed up our calculations whenever we hit the primal infeasibility or there are changes in the resource availability in the primal setup. That is going to be goal of our today's lecture. Now, the key idea here is that in each iteration, we fix the dual infeasibility when we were talking about primal simplex. Why? Because if you recall, when we were dealing with primal simplex, we decided entering variable, that particular variable which had the maximum negative sign, for example. Now, this negative sign is an indication of dual infeasibility when we were talking about the dual tableaus or dual constraints that we specified. Why? Because the negative signs that we had in the primal objective function will become part of the dual constraint. So, although we are making one variable leave and another variable enter, we are ensuring that we are always traversing the corners of this polygon or polytope, while ensuring that as we are moving from one extreme point to another extreme point, we are fixing the dual infeasibility, and this dual infeasibility automatically gets fixed as we drive our problem towards optimality, because our simplex tableau calculations stop when all variables have positive coefficients, and then we say that our simplex tableau has converged. Now, you see that initially we learned that why this particular variable would get entered, because if we are dealing with constraint like z equal to 3x1 plus 2y1 and so on, and if it is a problem of maximization type, we can clearly see that we can keep on increasing x up to infinity and z will keep on increasing. When we were dealing with standard forms, we were writing these equations as z equal to or z minus 3x1 minus 2y1 equal to 0. That is why we decided that the variable with most negative coefficient should enter, and that's why minus 3 was coming. And we will keep on doing that, updating our tableau until no negative variables exist in our solution, and that is exactly where we stop. That is when all the coefficients become greater than equal to 0. We mean that dual feasibility is now satisfied, and you can imagine that now there is no further way we can maximize this particular problem further, because if it is negative here, it means that if we have negative here, the equivalent of this z would be z plus 3x1 minus 2y1 equal to 0. Now, since this is positive, if you keep on increasing x1, your z is going to decline in the value. That is why this positive and negative you have to infer very carefully, because even in maximization problem we brought everything on the left side, and that's where we were saying that negative sign should be eliminated, and that's where we stop our iteration. So, this was a very quick recap of primal simplex. For detail, you can visit the previous lecture and go through the detailed calculations that we did. But here, since we have introduced the terminology around dual solutions, I wanted to put this into perspective, that how this primal and dual are also related to each other in terms of feasibility analysis. Now, we also learnt about the dual method, where we said that for every primal we can always write the dual. So, that is, if we had the problem of maximize Cx subject to certain constraint Ax less than equal to b, we can always write its primal form, where primal form would be minimize by subject to ay greater than equal to c. So, these two forms would be equivalent, and we also learned that if the solution from this particular set of equation is exactly same as this set of equation, we would say that the strong duality holds. On the other hand, if they are not equal to each other, we would say that weak duality holds. In case of linear programming problem, whenever we have unbounded feasible solution, strong duality is almost guaranteed, and that is where we take advantage of going from one form to another without resolving tableaus again and again. So now the question arises that since title of this lecture is dual simplex, why we really need another simplex method if we have covered all the cases earlier. Now, as I mentioned that in primal simplex, we keep the solution primal feasible and fix dual feasibility. On the other hand, in dual simplex, we always keep the solution dual feasible. That is, we make sure that all the coefficients are greater than equal to 0, but we may have the negative basic variables, which is primal infeasibility. So, we will try to fix this primal infeasibility and make sure that no negative basic variable remains in the solution. We will eventually discuss that under what circumstances such scenario arises. One very immediate scenario that we can think of, if that you have taken a primal problem and you have fixed that. So let us try to understand this with help of an example. Let us say that your objective was to maximize certain revenue. So you were selling certain amount of resource, and we can write this as C1 x1 plus C2 x2 all the way till Cn xn, and it was subjected to certain constraints such as A11 x1 plus A12 x2 all the way till A1n xn less than equal to B1, and we had m number of constraints. I can write this as AM1 x1 plus AM2 x2 again all the way till AMN xn less than equal to Bm. So again, a very simple straightforward optimization problem. You solve this problem entirely, and if you recall how you would do that, you will introduce something called as slack variable in each of these equation, convert it to canonical form. The moment you introduce this slack variable, we will convert these to some equality form. So if I introduce some Sm here, this again will get to equality form. We will go with the simplex method. Now let us assume that a condition happens that once you have solved your entire simplex method, your solution is now optimal, and your S1 and this entire constraint happens to be a binding constraint or a tight constraint. Meaning of binding constraint was that there is no slack available in this particular resource. This resource is indicating availability of machinery, let us say, and at optimal point you find that S1 star equal to 0. Again, a very usual case in optimization, that whenever a particular constraint happens to be binding, you would have no slack available in that resource because you have consumed that particular resource first, and that also becomes a limiting resource. So again, a very standard setup in a primal simplex, certain variables enter, certain variables leave. When we say certain variables leave, in this case S1 has left the solution and has joined the non-basic side and taken the value equal to 0. Now if this is clear, we would be very delighted that we have solved a problem of simplex method. Now another thing happens that in engineering, everything changes over time, be it profits that you are making, be it resource availability, and you would always be dealing with hundreds of constraints in real world system. So what may happen is that initially you were having B1 machinery, now some B1 plus delta B1 machinery is available. So a new resource has joined or new resource is now available. It can also happen that B1 reduce on the other side. So it may become B1 minus delta B1. Initially more resources were available, now less number of resources are available. So how you would solve from here? One straightforward way is that you solve this as a completely new primal simplex problem, which is certainly doable but time consuming, and would also result in wastage of all the compute that you have already done so far. Why? Because you went through the exercise of solving hundreds of tableaus if you are dealing with lot of corner points, and then suddenly one resource changed, and now you find that entire primal exercise became futile. And to avoid that, that is where simplex method comes into picture. That is how we would start from the last feasible primal tableau, and whenever some resource change happens, we switch to simplex in dual form and continue from here. You can argue why we cannot continue with the last feasible primal tableau. Why? Because resource has changed. The coefficients in the final simplex tableau of primal solution will have all positive variables. So there is no way you can decide an entering variable. That is why you have to search for a new way to express the same tableau without compromising integrity of the system. You cannot change the equations at your sweet will. So that is where we take the help of the dual simplex method. So again, a very related example that I have tried to put in more formal words, that you imagine a scenario that you are managing a water distribution network. After a standard primal simplex run, new rules tighten the capacity constraints. The word tightening means that it reduces the capacity constraints. Now the old basic feasible is now primal infeasible. Why? Because their slack was equal to 0. The moment you take any resource away from that binding equation, your slack becomes less than 0. So now your optimal solution has been driven towards the infeasibility, and hence we bring into the dual simplex method. We only fix negative basic variables. This should be RHS less than equal to 0 step by step while keeping the reduced cost in check. So this is a faster way for re-optimization, especially when we are dealing with large scale resilience planning where resources are coming and resources are going. The terminology that we will use in dual simplex also remains the same, or I would not say exactly same, but similar to what we did in the primal simplex. We would have an initialization step. I would not worry about this detail right now. We will go into the details of a solved example, and then we will revisit this slide to come in terms with what these terms do. There is going to be a pivot row. There is going to be a pivot column. We will perform the pivot operation and we will repeat. Now if you see, this is exactly what we did when we were dealing with primal simplex method. The terminology remains same. However, how we are going to choose this pivot row and pivot column is going to be a bit different in case of dual simplex method. Who would enter, who would leave is going to be exactly opposite thought in comparison to primal simplex method, and that would actually take us towards the feasible solutions. Another area where dual simplex method is useful is that when your original primal problem is actually infeasible. For example, if you look into this problem setup, you see here x1 minus x2 minus x3 is less than equal to minus 2, minus x1 minus 3x2 is less than equal to minus 3, and all variables have to be greater than equal to 0. If you recall, one of the required conditions in primal simplex method was that bi should be greater than equal to 0. Here it is exactly opposite. Now how you would go around this particular problem? The moment you multiply both sides by negative, this will flip the sign. This becomes greater than equal to problem. Then you have to go towards phase 1 and phase 2 and so on. So it becomes really cumbersome to solve this problem. So this problem, as stated, is primal infeasible and every primal infeasible problem is dual feasible. And that is where we are going to take advantage of this primal dual relationship. We will exactly solve this example using dual simplex method, because primal we cannot solve. So, we will go to dual simplex method and all the points of entering variables and pivot variables will become very clearer as we go forward. Cut. So, for this problem that we stated here, we will create a tableau as we were doing earlier for primal simplex method, but the way we will decide these entering and leaving variables, we will apply the dual thinking. So, tableau in primal form and entering and leaving operations in dual form. If you remember, in primal form, we were doing ratio test to decide the leaving variable, and we were checking the sign of coefficient while deciding the entering variable. So, this was all about primal. Let us move it somewhere here. This is fine. Now, as we have learned that primal and dual, they are related but reverse operations of each other. So, in case of dual, we will use ratio test to decide the entering variable, and we will use the sign test to decide the leaving variable. So, you notice the contrast here, sign of coefficients was entering, here sign of coefficients is leaving, ratio test for leaving, here ratio test for entering. Now, the reasoning is same, because when we go from primal form to dual form, we have to still ensure that all variables are greater than 0, that time in primal form, now in dual form. So, these two conditions is the condensation of that particular reasoning that all variables have to be greater than equal to 0, but rather than writing the simplex tableau again and again and again, we just change the rationale how we choose the entering variable and leaving variable. So, to make that particular point clearer, if you see, this was our maximization problem. The equivalent dual form in this case would be equal to, so we will have an we will write this particular constraint as this will become some minimization problem as minus 2y1 minus 3y2, where y1 and y2 are shadow prices now, and the constraints become y1 minus y2 greater than equal to minus 5 minus y1 minus 3y2 greater than equal to minus 35, and so on. Now, if I multiply both sides of this equation by minus 1 and both sides of this equation by minus 1, I get minus y1 plus y2 less than equal to 5, and here I get y1 plus 3y2 less than equal to 35. Now, this again becomes very similar to our primal simplex tableau, and we decide leaving variable that 5 divided by 1 or 35 divided by 3 and so on, and whatever is the lower value should give us the leaving variable or the entering variable in that case. So, we apply the same rationale in this case, that how to decide the leaving variable and entering variable without changing the tableau. If I change the tableau, I can still go with the same calculation, but remember here I am still dealing with the primal tableau. So, while I am changing the rules, I have to also make sure that I am not using the leaving and entering variable as per the dual tableau. So the tableau remains of primal and the rule changes, ratio test to decide who is entering and sign test to decide who is leaving. So if this is clear, in this particular tableau, the blue row is our objective function, nothing to do with that. We selected x4 and x5 as initial basic variables. The reason was we wanted our solution to be in canonical form. You see x4 is equal to minus 3, x5 is equal to x4 is equal to minus 2 and x5 is equal to minus 3 because everything else other than x4 and x5 are equal to 0. Now, who is most negative here? Minus 3, and it should leave our solution. Remember, in primal, the one with most negative coefficient was entering. Here, the one with most negative RHS is leaving. So, there is consistency in our explanation. Now, let us decide the entering variable. In primal, the one with least ratio was leaving. In that case, we used to write our ratios as B divided by A, where A was greater than 0. This was primal. Since we are doing everything opposite in case of dual, we will say that dual is equal to C divided by A, and this A has to be less than 0. So everything changes. B, C is the coefficients in the objective function itself. Why? Because objective function itself becomes part of the constraint in the dual. So we have to take its coefficients rather than the coefficients of resource itself. So here you see that these are the only two coefficients in the tableau that qualifies for ratios being taken. So we say that 5 divided by minus of minus 1, as per our formula, this ratio becomes 5. Here it becomes 35 divided by minus of minus 3, which gives us 11.67. In primal, the one with lesser value was leaving first. In dual, the one with lesser value will enter first. So 5 enters into our solution, minus 3 leaves the solution, and we do pivoting operation exactly same as we did earlier. If you quickly recall, anything outside pivoting row and pivoting column was updated as A is equal to A minus pivot column, pivot row divided by pivot element. So this 0 was 0 minus 0 into 1 divided by minus 1. So this value should remain unchanged. Everything in pivot row was divided by the pivot element, and everything that is in pivot column would become 1 here and 0 everywhere else. So I will not repeat these calculations. You may revisit the slides on Simplex lecture in primal form to see that how these particular tableaus are updated. Now let us see that after iteration 1 how the tableau for next iteration would look like. After all these calculations, you would have a revisited RHS, you would have revisited ratios. So again we will apply the same logic that the one with maximum negative RHS should leave and the least ratio should enter into the solution. Once we do that, we again get the updated tableau. Now please note that you may be tempted to make this minus 40 leave the solution, but this happens to be the objective function. So it should not be leaving your solution at all, but you should be choosing from the variables which are labeled as x1, x2, x3 and so on. So here you are left with this minus 0.75. Again 20 will enter into the solution, and after that you replace this x1 by x3, and in updated case, after all the pivoting is done, you would have RHS as positive here, and x2, x3 take this particular value, and your answer comes out to be minus 55. So no further iteration is required. This is the final basic feasible solution, which also happens to be optimal here, because after that you cannot move any forward. So the big takeaway here is that we started from primal infeasible. Primal infeasible gave us entry point to dual feasibility. Whatever was entry rule in primal feasible was exit rule in dual feasible and vice versa. So, entry and exit rules change their way. You can always look into the calculations here, but the fundamental remains the same, that one with most negative coefficient should leave, the one with most positive coefficient should enter, and so on. So, and this drives our solution towards the feasibility. Now, to put this together, this is where it comes into the case of infrastructure planning. I already mentioned that, but let us concretize this concept that infrastructure planners often face frequent minor changes such as new capacity limits, updated demand coming into system, and as a result of which the tighter constraints can invalidate the existing solution. By invalidation, we means that feasible solutions become infeasible given there is a small change in the resource availability. Now recall that when we were talking about Lagrange multipliers or we were talking about duality, we introduced something called as Y. I deliberately changed Y to notation of lambda when I was talking about duality theorems. This lambda also tells us the sensitivity of objective function to changes in resources, which was the interpretation of Lagrange multipliers, which is the interpretation of shadow prices in duality, and which is also the interpretation of why this dual method works whenever there is any change in resources, because all of them tie to the sensitivity of the objective function to changes in resources. So, with this introduction of shadow prices, we ensure that the old solution, wherever we left our problem, remains primarily intact and we don't have to keep on recalculating our W again, and hence this dual simplex comes into picture, which exactly starts from the point where our problem becomes primal infeasible. The earlier problem that we looked into was infeasible from the beginning, but if your final W also becomes infeasible towards the end, that doesn't matter. Your calculations will exactly start from there where your last feasible primal table was existing in exactly similar manner that we looked into. Again, another small example to further reinforce this concept, why it is so important for infrastructure planners and decision makers. Let us say that you are managing a regional water distribution network, and original optimization was to minimize pumping costs and it was subject to some pipeline capacity and water demand. Now, infrastructure planners and managers always deal with regulators. You designed a system for certain conditions and then some new regulation come, new environmental regulation came, new legislative regulation came, which said that now you cannot use more than this much amount of water or more than this much amount of resource. This particular problem is even more pertinent when we are talking about environmental infrastructures. That is, you designed a wastewater treatment plant and initially your discharge was going to a close by river. Now, an environmental regulation came that initially you were discharging some 5 million liters of water into that stream. Now you cannot discharge more than 2.5 million liters of water into that stream. Now you cannot keep on solving your system again and again to find the new feasible state. So that is where you have to start exactly from where you left your last solution or last feasible system. So what we do is that we start from the dual simplex, but it is important to understand that what has changed, why your primal feasibility is violated and why there is a need for the dual simplex method in this case. So here dual simplex method would quickly repair the negative slack variables without discarding rest of your CJ. So I see this role of dual simplex method as a repairer for the primal infeasibilities that stops or put brakes on your infrastructure planning problems. And why dual simplex is perfect for this? Because there are very few pivots. Within very less or finite number of operations, you continue ahead rather than going through n number of iterations that you already did. It works very well for large scale systems because in couple of iterations, even if you have solved hundreds of tableaus before, in couple of iterations, you would see that even for large scale systems, your dual solution would converge much faster because it has only couple of points to tap to repair the infeasibility that has come into the system. Remember the original example that we solved, both the constraints were infeasible. That's why we took couple of iterations to go there. But when we talk about real world infrastructure systems, in all practical sense, it may happen that one constraint is changing at a time. As a result of which, convergence in dual simplex would be way much faster than our original example, as a result of which we save the time as we do the calculations while preserving the dual feasibility. And dual feasibility is nothing but introduction of shadow prices and expressing our primal problem into a alternate form. So we can now conclude this particular discussion that dual simplex focuses on fixing primal infeasibility. In earlier version of this lecture, I spent some time on this fixing. At the end, I said that dual feasibility is repair of primal infeasibility. If this funda is clear, it becomes easier to appreciate why dual feasibility should be studied hand in hand with primal methods of solutions. It has great relevance for infrastructure managers, planners, where constraints keep on changing all the time, slacks may get more and more tightening and so on. And this has a particular great benefit when you are already went through the misery of solving phase 1, eliminating artificial variables, then solve the phase 2, but at the end somebody changed the constraints for you. You don't have to redo the tableau specifically when these phase 1, phase 2s have already been done, and it results in solving the time. Now here are two small exercises that you can think of itself that you should definitely try some small examples on dual simplex method. You may revisit the lectures on primal simplex method and try to change certain resources and see that how your solution converge when you redo entire primal simplex calculations and you do the dual simplex calculations from the last table that you made. You can also try to explore certain advanced LP solvers which implement dual simplex for real-time scenarios. So there is a library in Python that is called as Pulp. So Pulp automatically identifies when to solve the primal, when to solve the dual, so that the convergence to the optimal answers are much faster. In our subsequent lectures, we will explore one last milestone in this domain of linear programming, what we call as integer programming, which would build upon the concepts of primal and dual simplex, but that also becomes a very important concept in infrastructure planning and optimization. Thank you.